We'll start here with Connor Ward from the Imperial College of London, who's going to talk to us about pyop3. Connor, thanks for joining us. Take it away.
Cool. Right, hi everyone. So yeah, I'm Connor. I work at Imperial on the Firedrake project, which I'll tell you more about in a few minutes. And I'm here to tell you about pyop3, which was my PhD project, and I'm still working on getting it done and into Firedrake. So I'm going to tell you all about that today, starting with a bit of motivation, and then I'm just going to show a bunch of examples, basically, and hopefully get you excited. So this is joint work with my PhD supervisor and now my line manager, David Ham, and then also Jack was my PhD supervisor. So I'm going to very quickly talk about Firedrake, very, very quickly. So Firedrake is a finite element framework. So the idea is I want to solve a PDE using the finite element method, and I don't have an army of people that can do all the C++ magic. I am, say a PhD student, brand new to doing this sort of thing. So I am trying to solve the sign-positive Helmholtz equation here on the left. And if you want to do that in Firedrake, what you do is this script will do the whole thing for you. So you import Firedrake, you make a mesh, you make a function space. So here we're using degree 3 Lagrange elements. You create your trial and test functions. This is your coefficient. And then you declare your variational forms, which are exactly syntax. That's what these things are. They are exactly the same thing. And that is a symbolic representation of the problem that you want to solve, of your PDE. And then you just call solve, passing in those things. And one thing that makes Firedrake very special, so when you call solve, what happens is we go away and we will assemble those A and L, and we will then just delegate everything to PETSc. So this solver parameters dictionary here, which is very, very similar to the DeVito thing that Zoe was talking about earlier, you can pass anything you want through to PETSc. So if you want multi-grid or you want complicated preconditioners like PC patch or field split or any of that sort of thing, you can pass all of it through here. So Firedrake sits right on top of PETSc and is very, very tightly integrated. For example, so our Firedrake mesh sits directly on top of a PETSc DMplex. So this is great for people who don't have, it's an accessibility thing. So if you are new to finite elements and you want to have a simulation running quickly, Firedrake is excellent for that. I'm going to make a stronger point now, which is that if you want that having a code generation framework is essential for performance. So I'm going to reference a paper, again by Jack and David and Patrick Farrell at Oxford, in which they ran a Navier-Stokes solver on 2 UK supercomputers. So Isambard and Archer 2, which is the current UK national supercomputer. And this is just sort of the per node metrics for those two machines. And you can see they're very different. They have different architectures. They have dramatically different core counts and floating point operations, that sort of thing. And so in this paper, what they demonstrated was if you want good, strong scaling on these two machines, you need to completely change loads of really high-level aspects of your simulation. So on Isambard, you need the EBR element. You need a telescope multigrid for both. There's this SUPG stabilization, uniform refinement, additive stop, patches. But then on Archer 2, you need a different finite element with higher arithmetic intensity. And all these different things that you need to change. And this is absolutely the PETSc ethos as well, because PETSc give you these tools at runtime. You can switch all these things out and get the best thing that you want. But PETSc can't do all of these things. In particular, the finite element here, and also this term here, those are a Firedrake thing. Those are not a PETSc thing. So I'm going to focus my talk on sort of the Firedrake elements, what's going on here, and in particular what I do, which is everything but the maths. So I previously labeled this bit as not my problem, but I thought this looks better. So the core operation in finite element is this assembly routine. So I have, in this case, one input and one output. So I have a P1 discretization here. So I have 1 degree of freedom per vertex. And what I'm doing is I'm looping over my cells one by one. And then I take all of my degrees of freedom in the closure of that cell, and I produce an array with 3 numbers. So closure is, it's very convenient that Matt did his talk earlier because I'm going to talk about it. So we take the closure, we get our degrees of freedom, we pass it through, we do some computation, and then we get some result. So here, the result is going to be something in P3. And so we produce an array with 10 numbers, and we split it back out into the global vector. That is the core operation. So in pseudocode, it looks like this. So I'm going to loop over my cells. I'm going to read in what I've called DAT0, which is sort of Firedrake-specific terminology, but I'm going to read in my input vector and pack it into a local temporary of 3 numbers. I'm going to 0 my other one. I'm going to call my computation, passing in those 2 things. And then I finally increment in my global vector on the way out. So why have I called this bad kernel? I've included a quote from certain people here. So this is a great paper, which is the Firetran paper, Runtime Extensibility and Librarization of Simulation Software by some of the people here. So the quote is, in the case of fine-grained composition, the number of compositions grows combinatorially, but in any specific run, only a small number is important. Pre-compiling and dispatching, every combination leads to large compile times, bloated executables, confusing debugging, and compromises about which combinations will be made available. While a dynamic interface is far more maintainable, the performance overhead is unacceptable for certain applications. When the interface granularity cannot be increased to amortize the overhead of dynamicism, just-in-time compilation is an attractive approach to preserve strong encapsulation and debuggability. It's a bit of a mouthful, but what I'm saying is if I change my finite element, or like in this finite element assembly process, all the hot loops, all the performance is impacted by your choice of finite element, right? So if these are actually function calls, your performance is rubbish, because this is an absolutely critical loop, and you can't have any extra logic there. You need your compiler to be able to optimize these incredibly heavily. So we want to be able to code generate in here, because we can't use function calls. So the local kernel is the maths part that I talked about earlier that I'm not touching. I'm interested in the right, well, the 0 is trivial, and the increment. So what that is the global to local and local to global transformations that we need to do. So that's what pyop3 provides. So pyop3 is a DSL, domain-specific language, for unstructured loop stencil computations, and it manages this local to global, global to local transformations. It JIT compiles everything to C, and is part of Firedrake, but I also want to emphasize that it is not specific necessarily to Firedrake, and other people can use it, and I would be very happy if they wanted to. Right, so here's an example of some pyop3 code that is doing this sort of finite element assembly process. So I have all my imports at the top. I'm creating this is my local kernel that's doing all my magic computation that I don't care about, but it's reading in data and it is incrementing the result. This is your Firedrake script. And then you are looping over, so you have this op3.loop, creating, which is looping over the cells of your mesh, and then it is calling the kernel, passing in F and G, but because you're packing, right, you're taking your global thing and you're transforming it to the local thing, what I want is the closure of the cell to be indexed in this way. So this is, if you're familiar with NumPy, this is kind of the NumPy indexing style. So I've made this loop expression, and then I'm just compiling it. So, and then it can be executed and everything, but I just want to demonstrate what it looks like. So Here, we're dealing with P1 elements, so something like this. So in every closure, we're looking for 3 numbers. So the C code that we generate looks like this. So we have 2 temporaries. So yeah, like this is our packing temporary 0, reading in from the global data with a bunch of indirections. And then we are zeroing temporary 1, calling the kernel, and then we are incrementing the output back into DAT2. So we generate this code, and it runs. We can do more function spaces. So if I change my function space and I want to do P3 for one of them, all the code is exactly the same as before, but now G, the output, is a P3 element. So if we look at the code for that, it's a bit more complicated because pretty much all this bit at the top here should be unchanged from before. But after we call the kernel, we've got our packing loops for our cells, our cell, our edge, and our vertex. Right, so we can change the function spaces, and it's all automated. So you might want to look at this and go, well, you've got an indirection into an indirection into an indirection to give me an offset. That's rubbish. That's really slow. You're jumping pointers around. Your performance is rubbish, and that's true. So we're a compiler, so we can just optimize that. So exactly the same script as before, but at the bottom you say compiler parameters optimized true. And what does this do? Well, it takes that complicated, rubbishy indirection expression from before, it inspects it, and it just compresses it. So we end up with something like this, which has much, much better performance. What else can we do? We run in parallel. So this is MPI, distributed memory parallelism. And it just runs without change. Although the data structures are distributed, we use a PETSc star forest under the hood to do all the transfers. So the only change in this example here is when you're doing your assembly, you don't want to loop over the entire local mesh. You just want to loop over the ones that you own. So the only change is I want to loop over the owned cells. Everything else is exactly the same. Okay, parallel, we can also do matrix assembly. So what changes here is we have, I'm now saying G is a matrix. I'm not specifying how you make it. And then you want to loop over your cells, call the kernel, but this time G.M is the matrix, and you're passing in closure of the cell for the rows and closure of the cell for the columns. So this will give you back a little dense matrix per call. And then we compile it, and we generate code that looks like this. So you call your loopy kernel, and then we call mat set values, where we figured out all the indirections that you need. Right. So some other cool things. These are the more interesting things that we can now do. So that's all kind of existing PyDrake functionality that I've just re-implemented. This stuff we absolutely can't do at the moment. So what I've got here is an example that you might have in a sort of slope limiter type algorithm. So what I want to do, the loop expression I'm trying to express is I want to loop over every vertex in the mesh, and then for each vertex, I'm going to look at all the cells around it and do things with them. So in this case, what you do is you look at all the cells around a vertex, and you just say, well, the maximum number is what I put on my maximum cell number is what I put in my vertex. And this is hard because the number of cells that touch a vertex is not constant. So, for example, this vertex down here only has 2 cells that touch it, whereas this one has 7 cells. So what that means is we are generating code that have these ragged loops. So how do I write that in pyop3? Just like this. So I have a loop over vertices, and then I loop over the cells that are in the star, which is one of the dmplex terminologies, the star of the vertex. And then k equals 2 just means give me specifically the cells. And then I call my kernel, where I pass in my 2 functions. And this works. So the generated code looks like this, where pretty much the only thing that really matters here is you can see we have these two loops, but this inner loop has a variable extent where P0 comes from this, this input array that tells us the arity of the map. So what makes a lot of this possible in pyop3 is how I represent data layouts and how I can preserve topological information. So I'm going to give you an example here and just talk you through it. So I have here a mixed function space on a two-cell mesh. So I'm going to be storing a P3 element and a P2 element, which are two different spaces in a mixed function. And that means that my data layout is going to look something like this. So I've split them by field. So field 1 on the left, field 2 on the right. And you look at that and you go, right, well, there's a bit of structure there, right? I've got these two fields. So I can split them, right? So yeah, that's all I've done. But I can take it further than that. So we can also observe that. So this is the same split as before, but I've changed the coloring because we now have cells, edges, and vertices, and they're different. And dmplex knows that they're different, but it's very hard to retain that piece of information. So I've colored in the different entities. So you can see we've got a cell DOF, 6 edge DOFs, vertex, 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 cell, and so on. But there's structure there. So what we can do is we can transform that like this. So here we have, so we split this up, right? So we have cell, edge, 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 vertex, vertex, vertex. And then every edge has 2 degrees of freedom. And every cell has 1. And every vertex also has 1 degree of freedom. And then on the right, and then for the second space, we have some cells. The cells have no degrees of freedom. Okay, right. So we have a tree that describes our data layout. And what this is good for is you can see I've labeled them, right? So we've got field, and then mesh, and then DOF. We have this hierarchy. But if we take that, well, what we can do is we can flip them around. We can change our data layouts just like this. So just by flipping these things around. So what I've done here is, for every cell, there are 2 fields, where one field has 1 DOF and the next one has 0. Then there's an edge with 2 DOFs and 1. So I have completely changed my data layout, but the semantics are all unchanged. I've represented all the topological information. And this is great. Depending on your problem, you get totally different data locality properties. So one example that we've thought of is if you're doing LU on a mixed system, this might dramatically reduce the bandwidth, which would improve your performance. And there's a lot of scope for trying different things out here. So just to show you what this is like in pyop3. So I have a function on a P3, well, a mixed function space with P3 and P1. And I'm going to print the axes, which is an object that represents this structure that I've just described. So it's this structure up here that I've shown you before. And this is a textual representation of it, right? So I have a field, I have 2 fields, each with size 1. And then for each one I have like the mesh, right? So that's this one here. And then for the mesh, I have 0 degrees of freedom for my cells, 1 on my vertex, 0 on my edges, and the same for the other space. I can flip these around just by changing it in one place, right? So here, what we've changed is here, we've gone layout equals, and this doesn't quite exist, but it's very, very close to existing. You can specify your layout, and in one place, you can build up your data layout and specify it how you want, and nothing else changes in the code. We generate the indirections as necessary to get things to work. I've also been thinking that maybe we could be using PETSc options to drive this sort of thing, which would be quite nice.
Can I ask you a question about the implementation? This is very interesting. Is it implemented as a set of transformations that take one axis to another axis, or is it when you first create the axis, you kind of define how you're going to create it?
Yeah, when you create the axis, you define it. I mean, you could write a transformation path.
Transforms between one and the other, which would be, then it wouldn't necessitate ever having to say. You just sort of change it when you want to change it.
Yeah, I mean, changing it when you want to change it will necessitate a copy, right? Because you're changing where they all.
Oh yeah, totally true. Yeah.
So not completely sure how to expose this. So we can have a different data layout with different data locality properties, basically for free. This is the data layout that you would get instead, so it's just a slightly different variation on the same tree. And I think the last thing I was going to mention is we want everything I've just talked about, all these different things that we can do, they should, because of our code generation framework, be very straightforward to just port to GPUs. So the sort of hypothetical partial current implementation is just looks like this. So I'll define some device object representing my GPU, and then you just have this context manager that says, I want to do the computations within this block on the CUDA device. And so if you do that, all the C code that I just showed you will suddenly be CUDA code, all the function pointers, the array pointers that you have will be pointers to CUDA data, and we can transparently behind the scenes copy between the host and the device as required. So that's the pyop3 version, and then with FireDrake, it's exactly the same thing. So this will do the whole solve on the GPU. This basically works. So we've got a sort of proof of concept from Kaushik Kulkarni, who wrote his thesis in 2023, where he figured out how to do this with FireDrake, and he's done all the hard work and figured out, the sort of the auto-tuning performance stuff that you need to do to run for different, solve different PDEs, and depending on the GPUs and all that sort of thing. So it's all, we know what to do, we just need the time to do it. So like the dream is things like PC patch, which is I want to loop over my vertices, loop over my cells, solve a little thing, and that's my correction. We can write that in 10 lines of pyop3 code, and it will run on a GPU completely for free. That sort of thing is the dream. But yeah, that's the end of my talk. Thank you.
Any questions?
Chris?
So one quick one. The LoopI package that you pull in, is that external? Is that Andreas Glockner's package?
Yes.
Or is it, okay. What's it doing exactly? I was thinking the kernels would be generated by FireDrake, but it looked like some of them you were pulling through the LoopI.
So Loopy is a package where you have, it's like a sort of polyhedral compiler type thing. So we produce Loopy code, and then Loopy handle the transformation, the lowering down to C, and they also do CUDA and OpenCL, and so that's why we can do GPUs with not a lot of work, because most of the hard work is done by Loopy.
When you switch to your vertex-based assembly, I'm assuming that you're just hitting each element as if it's the first time. Like you're not. I mean, it's the way that we implement those types of schemes. We typically still have our element-based loops, and they do some of the work there, and then we do our vertex-based loops where we, essentially the element loops build something called like a transport vector or something like that. But I'm assuming, and that does like technically eliminate some duplicate work that happens when your vertex-centered approach hits each element, because each vertex. You know what I mean, I'm sure. But is that an optimization that y'all looked at or compared to?
I've definitely thought about that sort of thing in the context of sort of a DG style thing. If I've got cell loops followed by facet loops, and you want to tile the domain, that's absolutely expressible. I haven't done it, but I'm keen to do that sort of thing. With the vertex example that I gave, it's kind of a nonsense example because you can do it just by looping over the cells. But you can extend that to, for example, if I go back to it, if we imagine that instead of just setting a point on setting the DOF on the vertex, if this defines like a patch and you're solving some problem there, so you're doing a non-trivial operation per vertex, that sort of thing, you need to have this nested loop approach.
That'd be how you do patch. Right?
Sorry?
That'd be how you do patch.
Yeah.
So that's like some kind of vodka patch.
Mm-hmm. And if we want to, if you want to do a dense matrix or a PETSc matrix or all sorts of things, like we'll just generate that for you.
Okay, so that's a really interesting point. So what Patrick has these gigantic patches in some of his papers where dense matrices just don't work anymore.
Mm-hmm.
So how do you handle telling what type you want to target? Is it just an argument or?
I don't know exactly what I would be doing, but yeah, I mean, I have, some data structures are PETSc matrices behind the hood, some are NumPy arrays behind the hood, and like you can just change that and you just generate slightly different code, but it's all a compiler, so we just specify it at a high level and then I can figure out what to do from there.
Cool.
Yep.
So for this picture in particular, is it like a cheap flex, I guess in this case, operation to, given a vertex, find all the adjacent cells?
Yeah, well, we pre-tabulate all of that. So it's just a ragged array that we store.
So you pre-tabulate because he also has to filter it because star will give you everything and you just ask for cells. So I was going to ask you if you filtered on the fly or if you tabulated ahead of time.
Oh, we definitely tabulate all of it ahead of time, yeah.
You could do both.
Is the star thing like an O of 1 operation?
It is, depends what you mean by O1. You could say it's independent of the size of the mesh, yes.
It depends on the type of polytope that you're doing.
Yeah,
Okay.
that's right. And it can be a lot of work if it's big, but it's all low.
But if we did it on the fly, it would be too slow because there's all that searching that you're doing, whereas we want just the array to be looking into.
Because, you have to get the transitive closure in the graph. So it's expensive with transitive closure, but that doesn't depend on graph size.
Also, you get the orientations back, which means you're moving more data than I really want, that sort of thing. Yep.
All right. Thank
Cool.
you, Connor.
Thank you.